Welcome to the Electrochemistry screencast on corrosion and electrolysis. Now, one more thing to deal with in this screencast is something called corrosion, which is the oxidative deterioration of a metal. And any metal can undergo corrosion, and things like bridges and the metal parts on cars and boats all undergo corrosion, and costs our economy huge amounts of money every year. The most common example of corrosion is probably the rusting of iron. So when iron rusts, it looks like this, some links on an iron chain. And what's happening on a molecular level, on an atomic level, is you have a piece of iron, there's some water around, and oxygen dissolves in the water, and the oxygen undergoes a reduction reaction with hydrogen ion also in the water to make H2O. And that reduction reaction essentially drives, if you will, the oxidation of iron to iron 2+. And since metal is conductive, it can conduct electrons from where iron ends up rusting or corroding somewhere here in the drop. It can conduct electrons out to the edge of the drop where oxygen can easily gain those electrons. And that process has to have both water and oxygen. We often think about rusting as requiring water, but if there wasn't oxygen dissolved in the water or oxygen getting at the iron from the atmosphere, then we wouldn't have corrosion or rusting of iron occur at all. And if we look at our reduction potentials, here is the iron 2+ iron reduction half reaction, and there's water just below it. And for water to be reduced and make iron be oxidized, that's not going to happen spontaneously, at least not under standard conditions, because the reduction potential for iron 2+ is higher than the reduction potential for water. So iron is not more easily oxidized in this case, and that won't happen unless there's oxygen around, and oxygen is much more easily reduced than iron 2+, and so if we have oxygen around, this corrosion process will occur. And here's an example of what an iron nail stored in water that has oxygen dissolved in it looks like. And if you store an iron nail in water that has no oxygen dissolved in it, it actually stays pristine and does not rust. Now, how do we prevent or minimize corrosion? And there's several things we can do. One is you paint it, or you cover it in plastic. So you have you paint your boat, you have nails that have a plastic coating or screws that have a plastic coating, and that works to an extent. But once you cut through or scratch through the paint or the plastic, then it doesn't work very well. You can galvanize things. And galvanizing is coating with zinc. So if you go to the hardware store and get some galvanized nails, there'll be nails that have been coated with zinc. And the reason for using zinc is because it's more easily oxidized than iron. So the coating will oxidize rather than the nail itself until all of the coating is gone. And since the zinc is conductive, so long as it's in contact with the piece of metal that you're trying to protect, it will be protected. And then the other thing you can do is connect your piece of metal that you would like not to be oxidized to what's called a sacrificial anode. And it's kind of what it sounds like. It's an anode, so it's something that undergoes oxidation, but it's sacrificed. It's more easily oxidized than the thing that you want to protect. Oh, and before we move on, I should just note the first two are called Anodic Protection, and the last one is called Cathodic Protection, because you're essentially turning your piece of metal into a cathode, by connecting it to something else that functions as an anode. And here's an example. We have an iron storage tank. We'd like it's buried underground. We don't want it to rust. So we put a piece of magnesium, which is more easily oxidized than iron, in the ground, connected by a wire or something conductive to the iron storage tank. And what ends up happening is the magnesium ends up being oxidized, and the iron that would have been oxidized does not undergo an oxidation until all of the magnesium has undergone that the oxidation, and it's pretty much all gone. The reduction half reaction is the one we saw before for the corrosion of iron. The main theme for the rest of this screencast and the remainder of this unit is to note that although we've mostly been looking at spontaneous processes, spontaneous electrochemical processes so far, if we add energy, if we add enough energy, that is, to a non-spontaneous process, we can make it happen. And we will do several examples of this, starting with the production of chlorine gas from chloride ion. And here is an electrochemical cell where we have two half cells, of course, and we have some chloride solution on one side, water on the other. We have an anode and a cathode, and the chloride ion can conceivably be oxidized to chlorine gas, and water can conceivably be reduced to hydrogen ion and producing hydroxide as well. And so if we can make this happen, that would be a good way to produce chlorine. Well, here are the necessary half reactions for this to occur. Chloride ion making chlorine gas, water making hydrogen, and looking at the reduction potentials chart and getting the appropriate E-naughts for this and adding up the two half reactions. And what we find is we get an E-naught of negative 2.19 volts for this process. And of course that means that this reaction that we want to happen is not spontaneous. It has a very negative E-naught value for the overall reaction. But we can make this happen via a process called electrolysis, where we use an electric current to drive a non-spontaneous process and bring about chemical change. So instead of using the reaction or writing this reaction and saying, hey, it's not going to happen, it's not a spontaneous process because it has a negative E-naught, we hook it up to a power supply and we force current through it, and we force the electrons to go in the direction they, quote, don't want to go, and make the reaction occur, even though it's not spontaneous. Therefore, a big idea throughout this whole unit is that reactions can produce electrical current, or they can bring about chemical change. And we've seen quite a few spontaneous processes that produce electrical current, but if we run electrical current through a process, we can make a chemical change occur that we might be interested in. And then one other big idea, which we've dealt with quite a bit so far, but it's worth reiterating, is when we look at a possible process, we have to consider what's available, what's most easily oxidized, and what's most easily reduced. And of the things that are available, the most easily oxidized substance will be preferentially oxidized. The most easily reduced substance will be preferentially reduced. And this happens whether it's a spontaneous process where these things happen naturally, or a non-spontaneous process where we force them to happen. Still, whatever is most easily oxidized will be oxidized, and whatever is most easily reduced will be reduced, as a sort of general rule. And that's it for the corrosion and electrolysis screencast.